Hello everybody, my name is Afshin Majd and today I'm going to present a few slides on the topic of grid interconnection studies for renewable energy using EasyPower. The purpose of this work and presentation is to show how we can utilize EasyPower in simulating the renewable energy. There would be a small project that I have put together, and we will go through the details of it and the techniques that are needed or required to use in order to model the renewable energy power plant. Mostly the work will be focused on the power flow. However, I will give a little bit of history on how we can deal with this type of projects and what requirements are needed in terms of the FERC and NERC rules. What are the standards that are applicable to any renewable energy that gets connected to grid. The purpose of the study is number one, compliance of the plant with the 2C and to evaluate the compliance of the plant with the applicable local code, compliance with FERC NERC requirements, performance of the plant in terms of the power factor at the point of common coupling, and also equipment sizing and equipment evaluation. And by equipment sizing and equipment evaluation, I mean we want to in fact come up with a size for a reactive power compensator if the plant needs any extra reactive power compensator. So if we perform these studies and then we come up with the solution and the conclusion that there is no extra reactive power compensator needed, then the plant is just good and we are complying with the requirements. Now, let's just take a look at the FERC requirements in general. For those of us that have enough background and familiarity with FERC and NERC requirements, FERC obviously is the Federal Energy Regulatory Commission, and NERC, North American Electric Reliability Corporation, and NERC is an entity which assures the reliability for the bulk power system for the entire country. Of course, NERC covers entire United States and part of Canadian provinces and also part of the Mexico. But we focus on the general rules of the NERC, and this project could be anywhere. But the work that I present today, it could be a small project, a large project, and anywhere in the United States or even outside of the country. Another background and maybe explanation that we need to have prior to starting the work is that the renewable energy projects, they can be either a distribution level project or a transmission level project. Distribution level projects usually get connected to systems at smaller than 69 kV, and their size is less than 10 MVA, and transmission level projects are larger than 20 megawatt and they get connected to 69 kV or higher. So these are the criteria that we need to keep in mind in order to separate and distinguish a distribution project from a transmission project. That's one thing. The other issue for this presentation is that I'm going to focus more on the transmission level projects because they tend to be larger. They tend to be type of project that require a detailed study work, and of course the impact of the budget. And then because they tend to be larger, they need to be studied in a lot more details, and the result of those studies are going to be more important, because eventually if there is a little bit change in the size of the compensator, of course it translates to more dollar value. But FERC order number 661 requires public utilities that own, control, or operate facilities for transmitting electric energy in interstate commerce to append to their standard large generator interconnection procedures and large generator interconnection agreements in their open access transmission tariffs standard procedures and technical requirements for the interconnection of large wind generation. Details of the requirements. In a very simple language, the requirements for the FERC standard or FERC rules, I can break it down to three important high-level requirements. However, I will pick one and I will focus on the third requirement here. and that would deal with the power factor requirement of the power plant, and we focus on that work. But number one, demonstrate that the plant owner or the plant designer or a developer has to demonstrate low voltage ride-through capability. In other words, show that the plant can remain online during voltage disturbances up to a specified time periods and associated voltage levels. What it means is that if there is anything that brings the voltage at the terminals of the power plant to a very low voltage or zero, the plant should not trip for a certain number of time or a certain number of cycles. In other words, for 9 cycles, I mean, there's a specific language in FERC that requires the plant to be connected even if the voltage of the plant drops to a very low value. We call it low voltage ride-through, or in other words, the plant has to be able to ride through that low voltage conditions. Number 2 is that the plant has to have supervisory control and data acquisition capability to transmit data and receive instructions from the transmission provider. This is a SCADA requirement and outside of the scope of this presentation today, so I'm not going to focus on that one. Third would be maintain a power factor within the range of 95%, leading to 95% lagging measured at the high voltage side of the substation transformer. Now, this is the requirement that I'm going to focus on today, and this requirement does not ask for a fixed power factor operation of the plant. Instead, it's just asking for the capability for the plant to have the capability to be working within 95% power factor to plus 95% power factor. And someone may ask why these requirements or where these requirements come from, even though again it doesn't really concern our discussion today. But this way the system operators in fact make sure that the plant has enough reserve of reactive power in case there is a transient voltage drop or voltage increase, because those are the scenarios that you will need either to inject reactive power to the system or absorb reactive power from the system. Now, if you have a very, very stiff grid, you will need a lot more injection or absorption from reactive power in order to be able to shift that voltage. But anyhow, that's the leverage that the power plant has in order to be able to shift, pull or push the voltage at the point of interconnection. Now, the discussion, next important discussion would be how we define the point of interconnection for the plant and how we can make sure that we can comply with these requirements. These requirements have a lot more technical details into them. I have started from FERC and NERC, but basically the entire country, United States, is divided to different regional ISO and TSOs. They all develop their own codes and standards, but they all start from the base and level that NERC puts the requirements. So it means that they can have requirements which are more stringent than NERC requirements, but they cannot have more relaxed rules and standards from what NERC requires. Now let me just move to the next slide here, and that makes it a little bit more clear for us. This is a snapshot of the project file that I put together. This is of course a very small wind power plant. The way I have modeled it as 5 synchronous generators here. We have a collector system, cables, a step-up transformer, and of course POC, point of interconnection. Now, as you see, I assume that there is a transmission line. So there is a transmission line here that connects the point of interconnection actually to the rest of the transmission system, which we show it as a utility. But sometimes this POC can go and be on the other side of the transmission line, in which case we have to also be very careful about the stability of the system, because whenever we push a significant amount of active power through some transmission systems, depending on the impedance and capability of those transmission lines, we might face a stability issue. But other than that, what happens here is that there is a step-up transformer, and if this is a transmission level project, something subject to FERC 661, then we will be definitely having the definition of point of interconnection at the on the high side of the transformer. There are occasions that you can define the high side of the transformer as POC for some requirements, and for the rest of the requirements you can define the low side of the transformer as POC. Those are areas, some provinces of Canada deal with those requirements, but again, bottom line and the point and focal point for this presentation is that we're trying to show that how EasyPower can be used, how it can be utilized to model the system, and eventually it really wouldn't matter for us as long as you have the model. It wouldn't matter for us to have the POC on this side of the transformer or low side of the transformer. So now this becomes the collector system. These are the machines, and this is the rest of the system. Now let me just open up the real file that I've created here, and this becomes the system that we have here. The main transformer, machines, 1, 2, 3, 4, 5 of them, and the rest of the system POC defined here. And of course it's ready to go because I created this file, and then maybe in the future I can even go into details. If there is a chance, I can go into details, future presentations, and then show how this file or how the details can be entered here. But just general description, if you have 5 of them, or if you have 10 of them, or even more, it really doesn't matter. It would be a fact of creating these wind turbine models here, and then you can copy and paste them as many times as you want to. This is ready to go. I run the load flow. You see the load flow results here, and within like a few minutes from now and a few slides from now, I'll show you how we can extract and use the information. But before that, let's get to the fact that what exactly FERC is requiring us. So what they say is that, let's say if you want to be able to meet the 95% power factor plus or 95% power factor minus at this point, it means that for a 100 megawatt power plant, you should be able to have to inject 33 MVR or absorb 33 MVR at this point of interconnection. That's what it means. If you go to, let's say, 50 MVR, 50 megawatt, then you will be required to generate or absorb half of that value, which is 16.5 MVR, either on positive side or negative side. That being said, there are some ISO and TSOs which will allow you to make up for any reactive power losses that gets wasted or gets lost from the time that it gets generated here up to the time that makes it to the point. Again, I'll leave it maybe for another opportunity here, but for now I only focus on the fact that measure the power factor here, and then how we can make sure how we can use this tool and this software to see if whether or not we meet the requirements. Now required steps that we need to take in order to put the project together and collect the data and be able to run the system is that, number one, we have to collect the main power transformer data, or MPT. That's for sure a very obvious issue, because you will have one step-up transformer, then a step-up transformer is going to play a very important role in terms of how much reactive power gets to the point of interconnection. You need to see how much gets absorbed by that transformer, and if the transformer impedance goes up or down, or the voltage level goes up and down, how the transformer, if you don't have the correct and enough information about the transformer, basically it's going to invalidate the entire study work. So next one is collector system data, cable length, and impedance. We will need those information as well for very obvious reasons that you need to model it, and again, like the transformer, they're going to play a role in how much reactive power gets consumed by that system. Then exact location of the point of connection, POC or PCC. For that, we will need to know the definition of the PCC. Obviously, it's a transmission project for the sake of this discussion, and if it's a transmission project, it has to be, the point of interconnection has to be on the high side of the transformer. nominal operating voltage of the system. We need to know that one. We will see the results, and we will notice that changing the voltage within, let's say, 10% tolerance, which is usually the norm, can significantly impact the value and capability of the plant to meet the FERC requirements. Now, going back to this point here about the PQ curve of the plant, the first thing, we need to know all the information of the turbine. Each turbine comes with a data sheet, and here I just put together a imaginary, in fact, I would say, PQ curve for a turbine which is from manufacturer, let's say XYZ. That really doesn't matter here, but I put this curve together, which I built it up myself, and I'm going to use this one, assuming that the manufacturer of that turbine has provided us with this PQ curve. So we have this PQ curve, and we want to see how we can utilize it if we wanted to model the system. What it says, for those of us that maybe have little less background and history in wind area, it says that the turbine starts from zero. At zero power production, it has zero reactive power production. Then 100, let's say for 100 kilowatt, it can generate up to 500 kVR. 200 kilowatt, it can generate up to 500, and 650 kilowatt, it can generate up to 500 kVR, and so on and so forth. Anything, this is actually the borderline which tells us for each P value how much Q maximum we can get out of the machine, or the machine can absorb. So these are actually, any point within this area can be operating point, and these borderline values are the values which are the maximum numbers. We will be dealing with this borderline because we are looking at two extreme power factor requirements. That's one reason. You don't want to go pick up a point here while it doesn't give you much information, because it doesn't tell you the extreme reactive power capability of the machine. So these are 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points that we have to put into the system. Now let's go back here, open it up. Obviously I will need to create 11 scenarios or even more, depending on how precise you like to model the system, but 11 would be the minimum that I recommend here. But if I open up one of the wind turbines here, as you see, let me see, go to the database, open it up here. As you see, power flow, they all are put in PQ mode, because we are looking at we are going to focus on how much P and Q this wind turbine can generate, and how much reactive power, or how much power factor we can get at the point of interconnection. So here PQ mode, and the megawatt is 1.8, MVR is 0.6. So let's go back. 1.8, 0.6 is exactly this point. I consider this point as the full or rated operating point of the machine, which means that machine is generating 1.8 megawatt, and also generating 600 kilo kVR. Along this line 1.8, it can actually generate or absorb any value of reactive power along this line. Could be any of these values here. Now, when it comes to EasyPower modeling, since these plants usually have a large number of turbines, the best will be creating one turbine with all the required data and copying it for as many times as needed. This will significantly reduce the modeling time and eliminates any risk of human errors. For the power flow studies, you will need to choose the PQ mode, as you saw, for the turbine operation. But let's just take a look here. Once you have the data and PQ information of the generator, you can enter it here, as you see. Oh, let me just go. Yeah, you can enter it here. As you see, 1.8.6, obviously that would be one scenario, but let's say that you're just creating the model here. So you will put all this information here, you close it, you go to here, and you copy it, and then you paste it. Comes here, and this can be connected anywhere you like. You can just do it 10 times, 15 times. It just creates that system for you. So now for the cable side, because these are wind turbines, so you would assume that these cable lengths are not going to be the same. Obviously, even the type might not be the same. So for that, you can either create the cables later. That's one way. So just copy paste the turbine side, or you can in fact have the cable there with one specific type, and maybe later on just open it up, go, let's say, to next table. If they all are the same type, you can change the length. That's one way. If the type are different, which is less likely, but anyways it might happen, you can just make the changes here, or just create them from scratch if you wanted to do for all of them. But I would recommend you can just copy paste and then go to them one by one, because once you create all of them and connect them to the collector system, you double click on that one, you can see you can just cruise and go from one to another by just clicking a button and then make the changes instead of going to here and dropping in a cable. And next slide. So this is a screenshot of the turbine, one turbine, and its values. And it says a screen capture of the turbine editor page. As you see, it has to be in PQ mode, as I mentioned. The base kV is 69. Again, one explanation about this side is that all this value is that all these turbines come with their own transformers. When they have their own transformers here, then there would be a low voltage side, there would be high voltage side, which is 34 kV, 34.5 kV. And again, you can just completely model this part as a package and then copy and paste it. So again, this could be different voltage. It could be 1000 volt, depending on the type, depending on the manufacturer. But however value it is, it really wouldn't change the way we use EasyPower for modeling purposes here. So I take it to the other monitor, and you see, because I picked this point 1.8.6 MVR, so that's what I input here. That's my operating point. And then next after this is here, it comes to creating the scenarios. As you see, we will need to create at least 11 scenarios, as I explained before. There are a lot of information involved here, and there is a lot of information you can get out of EasyPower, but it really depends on how detailed you want to model it here. This is, again, I probably skipped a significant amount of modeling here and work, but I can just show you just a few slides, or a few screenshots of how this value or these numbers were obtained. So if I have 5 of these turbines here, so 5 turbines, 5 transformers, a step-up transformer, and I am going to run it for, let's say, one of the, let's first take a look at the table, how the table was created. 0, 0 was one of the points of that PQ curve, which if you want to look at it again, it would be here, 0, 0. So I'm just picking up these points, as you see, one by one, and then you can double check it yourself also. But 0, 0, the other point is 500 kVR and 100 kilowatts. So 100 kilowatt, 5 kVR, 650, 500, 650, 1000, 1400 kilowatt, 1000 kVR. All these points are for the individual turbines that I put here. Now, we have 5 of them. If we have 5 of them, so the plant typically has to, or rated value of the plant when each turbine is doing 100, the total plant has to do 500 kilowatt. But we all know that we are not going to get this much active power at the point of interconnection. So what it means is that we will get less than that, and that's going to be 492 here for this case. And so we have 492 here, and again, If each turbine does 650 and we have 5 of them, then 3250 would be the total power generation of the entire plant, and the kilowatt that makes it to the point of interconnection is going to be 3231. Again, that can give us the efficiency. The other important issue we have to keep in mind is that these are the rated values, and I just made one column for P, which is the measured P at V equals 100%, because as you see, you have to repeat these scenarios for V 100%, V 90%, and V 110%, because change in the voltage of the point of common coupling will impact the amount or the capability of the plant to absorb or inject reactive power. So we have to keep that in mind, and then you can make the comparison and see these all come from EasyPower. These numbers all are the result of the simulations that I have done for different scenarios. And if you see for 100% KVR, let's say for the same generation you get 2277 kVR at the point of interconnection for V 100%, and for V 90%, as I mentioned, you would expect the same plant, the same generation for each turbine delivers a value less than 2277, and you see it's 2219, so it has come down. And eventually when you put all these values together, let's just take a look at some. The best would be, and what I recommend is that to create this P under each voltage level. So this one in fact corresponds to V 100%. So my recommendation is to create one also for V 90%, one for V 110%, which obviously is not here, but I show it in another slide. The numbers for P value between 100 and 90%, they are going to be very close to this, but there is difference. So if somebody wants to really perform a good detailed study, it's better to model it as well. And now I go back here. What you see is, for example, I pick up 1 point. Let's see, this is base scenario, but as you see here, I will have 1, 2, 2, 3, 4, 5, 6, 7, 8, 9, 10, and one base scenario. So I have 11 scenarios. For those 11 points, can be more, but this is the minimum again that I recommend. And if I go here, open it up, power flow, PQ mode, for here we have 1.8.6. let's run the load flow, run it. You see the values here, and I go to power flow options, I go to kilowatt and kilowatt, I would say apply. Okay, let's just check it against that table just for the sake of, because it's important for you guys to follow what I've done here. For example, for this point, this is the point that we are simulating for V 100%. Let me see if it's V 100% here. Yeah, in fact V is 100% here, so the value should be closer to 8897, and it is 8898. So this comes from this simulation here. It is 8898 almost. You see if you round it up, so that's exactly what shows up in that table. The value for Q is 1717, 1717, and that again is this working value, and you see exactly we get the same value for Q. So these values have been summarized. That's how they get generated and then get summarized in this table, as you see. Then the next step that you will need to do is that perform, and again we can just do another simulation for, let's say, 90%. So for 90%, let me just go here, change the value to 90%, click OK, and run. In fact, it's already run. It's just updated the simulated results. So now you would, as you see, this value has come down, and you have to create, it's better that you create a separate P column for V 90%, because this one really corresponds to V 100%. But let's go back. This is 8875, which you see it has come down slightly. So again, another the importance of creating another column for 90%, but let's focus on the Q because that's the important part. And Q becomes 1431 here. As you see, its previous calculation has been 1430. It comes out to be 1431. So this value is slightly different, but you know, depending on simulation and the values that you put there, you should be able to get like closer to 1430. Now, the one important point to pay attention to is that, as I mentioned, when the voltage comes down, I haven't changed anything for the turbines. They are the same turbine, the same generation here, but the value of the Q comes down, and it comes down significantly. What it tells us is that if your utility voltage drops, then you will have to somehow come up with a solution to either increase the size of compensator, or at least keep in mind that your plant, which is the same plant, the same generation for Q, less amount of Q makes it to the point of interconnection. And that's exactly what EasyPower helps us to conclude. Otherwise, it's just you can't do it by hand calculation. You may know the trend because we know that the voltage and the reactive power are related, closely related, but in order to have an exact value, you will need to model it, and you will need to run this simulation, and that's exactly the point that I'm raising here. You use EasyPower to get these values the way they show up in this, and then you go for these 11 scenarios. Q are here, then you do it for V100%, V90%, then it comes to the fact that you have to now put the requirements of the FERC here. What it says is that you need, for each P value of the plant, you need to be able to absorb or generate enough reactive power to have a power factor of 95%, either way, plus or minus. Now, let's just, reactive power of 95% translates to 33% of your active power. And by active power, I won't look at how much active power makes it to the point of interconnection. I would look at the rated value of the plant. Let's say if each machine is working at 100, the rated value of the plant is going to be 500. So if that's 500, that means 500 multiplied by 33, that would be 165. You will see 165 here. There is the same relationship between all these numbers here. So that becomes my reference. That becomes how much reactive power I need to have at that point of interconnection in order to be able to meet the FERC requirements, and that's how much I generate. So let's say for 500 kVAR, I generate 2428, I will need only 165. I generate 2403, I will need only 165. And these values is the surplus. As you see, they are negative. So this value negative, they start coming down as the active power goes up. Or in fact, let me just go back here. As we start moving along this axis here, and then P goes up little by little, you will see that the requirement, because this line, this power factor line, starts kind of going up, and that's what you see. You get closer to critical points. So this value is negative, 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 and eventually it becomes a positive value. That's where we notice that there is a reactive power deficiency. Now, logically, you would compare your worst case scenario, which means V90%, against this value. However, this is what I've got from comparison between my V100% versus my 95%. Again, this is a way to present how you can solve this problem. You, from this point on, using your engineering judgment and understanding the FERC requirements, you can just change it any way you want. But that gives us a 1207.63 kVAR, the required, at least the minimum size for a reactive power compensator that you will need here. And then that brings the next discussion, that do we use a switching cap bank, do we use a SVC, do we use a STATCOM, or do we use a synchronous condenser? That all depends on the type of reactive power deficiency. That all depends on the language of that specific ISO, TSO, and that specific regime, and also country, However, it's not going to change anything with regard to your simulation. You still use the same tool, you still get the same results. Now, let me go to the next slide, and it says calculation of the cap bank size. The largest difference between the supplied and the required reactive power at the point of interconnection will provide us with the size of the cap bank. So as you saw in previous table here, all these numbers are the difference between how much you generate, how much you generate here and how much you require, how much you need to have here. You see this number drops below this number, and this is the difference. You see this number is even lower, so you would expect that the size of the reactive power compensator goes up for this calculation, and you can just obviously calculate it yourself. Now, these calculations have to be repeated for the rated voltage plus minus 10% for this voltage, which is very, very important. So I mentioned plus minus 10%. I'm assuming that the tolerance of the voltage is 10%. It could be more, it could be less. I would really doubt if it's more, but there is a chance that sometimes it's at transmission level, it's a narrower range for the voltage, and you would know the trend that if the voltage goes down, there would be more need for a reactive power compensator. So if you don't have much time and you just want to go straight to the worst case scenario, your worst case scenario would be one when the voltage is minimum, bottom line of that tolerance, voltage tolerance range. But basically here I can change it to for each scenario that you run, and let me just go, maybe just for the sake of this discussion, open one of the scenarios database. Go to scenario, open a scenario, continue, and let's say choose this guy, open, and let's just take a look here. So what has happened here is that, let's just take a look at what point is it. This point is 100 kilowatt and absorbing 500 kilowatt. So if I close this one, if I go here, if I go back, if I look at this one, 100 and minus 500. This is this point here, as you see. That one of the scenarios, because if you remember, I mentioned that for each point I have one scenario. So come back here, or let's actually go to Excel sheet. This is, oh, I don't have it here, so let me just pick up a scenario that I can compare the results again. This is just a screenshot part of that table. Let me just choose another scenario that has a value. I go to Scenario Manager, and choose maybe this one. $650. So here we are generating 650 kilowatt each machine, and generating also 500 kVR for each machine. And for that, $650 and 500. This is the point. So what I have here is 3250. What I'm showing is that 2277. I'm sorry. I would expect at 100% that only 31 kilowatt or around this number makes it to the point of interconnection. And for that, I have to go here and run this guy. 3227. It's close to, oh, it's 90%. So let me just change it back to 100% so that we can make that comparison. 1 per unit. Click OK. I run it again. It becomes 3231 here, and we get 3231 here exactly, equal, we get 2277 for this scenario uncompensated. 2277 uncompensated, as you see. So that's how I generated this Excel sheet, and that's how I got this model here. Obviously I can change the voltage and then create more, but that's, you know, base scenario and one scenario here, so it should be pretty obvious now that how this work can be done. Now I go back and continue. The voltage level, as seen, at lower voltages the plant shows less capability in meeting the power factor requirements. Larger compensator will be needed here. Then table for the scenario results. For the scenario results, this is the table that we have here, and so we have kVAR values, kW values, very much like what we had before. The difference is that now I have added the voltage of 1.1 per unit here. So I used to have 1 per unit, 90%. This is actually a more complete table. What matters here? Again, the same method has been used to extract this information, but I would like to draw your attention to the fact that Q, when the voltage has gone up, capability of the plant to generate Q has gone up. Let's look at this 2219 versus 2277 versus 2322 when we go from 90% to 110%. So keep that in mind. And then required cap bank sizes, which I believe I compared only the V at 100% versus 95%. And these are the numbers. It really doesn't matter. I would highly recommend that you add the losses, you add the efficiency, you add the transformer losses, all those things to this table. And if it's a complete report, why not making it like something that includes every detail and perhaps provide the people who have to make the key decisions with more information. Let them know exactly what's going on inside the power plant. Once it's just one click away from the results that you have here, you can just go to power flow options, run the different numbers and different options, and then get the values that you want. Let's just go back to EasyPower for a second and do a little bit of experiments here. I go to database, edit. I would say yes. I would go to scenario manager and I open the base case. I would say no. Here what I'm going to do is that go to power flow here and run the power flow. Now I'm gonna go change it to 100% here. Take a look at the size of the cap bank, because now that I estimated the size of the cap bank, I can add it either on this bus or on this bus. Technically, it has to be added on this bus because we did all the calculation at the point of interconnection. However, when it comes to construction and real world, a lot of times it would be more convenient, it would be easier, and it would be less expensive to add the capacitor to the collector system, to the collector bus here. And for that, I haven't changed the value of the cap bank. However, when you do that, there would be a little bit of fine-tuning because you did the calculations here. What matters and what is really important is that you have to get a power factor of 95%. So now I will look at the power factor with and without this compensator, because now that we have the calculation, we have to show to the people or the committee, the review committee, that it really works. This is really the value that makes the plant to work, be able to provide enough reactive power so that your reactive power factor goes to 95%. For that, let me just run it here. I get this value, 98.2%. Then I go to open and I look at the power factor here, 95%. Exactly 95%, and exactly that's what our calculation showed. It cannot be any better than this. You are wrong exactly on this one. And just let's just, for the same case, I open this guy up, I put the same cap bank now here and run the system. It goes slightly lower, and you would think that we have issue meeting the requirements. In fact, we are providing more reactive power than needed. That's what's happening here, because your reactive power value is a cosine value. If it goes lower, it means that the phi, the angle, has gone up, and if the angle has gone up, it means that for the same amount of P, you're providing more reactive power. So just as an example, if I again open this guy, go back here, close it, just to prove my point, I go here and I put this guy, let's say 1.4. What I'm saying is that this power factor number has to go down. I say okay, I run it, it does go down. And that's, again, if you put the same MVR here. So in fact, if you put it on the low voltage side, you need a little bit of fine tuning. You have to make sure that, or if it doesn't really matter, you can use as an initial point, you can use the same value that you calculated here. So again, I open this guy, this system is again uncompensated system. Go back here, the values, and I go to next slide. Now, this is a very important slide. In fact, it summarizes all the work that we have done so far and shows us exactly the points that we put together. Let's say for here, we have 11 points and 3 plots plus the power factor requirements that are here. So this color is for 110% voltage not compensated, color for 90% voltage not compensated, power factor 95%, power factor 95%, both sides, and 100% voltage not compensated. So here it's very obvious that you can see as the voltage comes down, for the same amount of power, the plant is able to generate less reactive power. You see this color is associated with 90%. This color is associated with 100%. And this color is associated with 110%. And it comes down. And these are the power factor requirements that you see here. And this obviously would be the reactive power deficiency at this point. So we have this much reactive power deficiency. And if I personally compared it against this 100% voltage, but the good way and better way, in fact, would be comparing the deficiency and the requirement versus the 90% requirements here, which would be a larger number. So this is the curve, and as you see, the voltage comes down. The curve seems like it's shifting down, and that's how we meet the requirement. Now, on the other hand, if you look at the absorbing requirement, absorbing reactive power requirement, the plant very well meets this requirement. There is no concern. You would not have any concern. It absorbs way more than what the requirements dictate. So you don't need to put anything in this area. If you have any compensator on this area, obviously it's going to be turned off and not utilized for when you're in absorbing reactive power mode. So now this is the same plot after addition of the after addition of those compensators. So what we have done is that we have added the cap bank, we have turned it on here, like very much the scenario that I discussed. I close it, I have added it here, and it changes the power factor here. Now for each point of those 11 points that we had, I have turned on this value and I have regenerated the values to the Q values to plot this curve. Let's go back. Sorry. Here. For each of these points, I have one Q not compensated, one Q compensated. This Q compensated is after the addition of this cap bank, which obviously is not. It has to be rounded to a practical value, to something which is available in the market. You have to round it to that value, and it provides you with Q compensated values here, which is the next column, as you see. No. This one. Looking at the plot here, you would notice that still it seems that we have a little bit of deficiency issue, and that brings us back to the point that it could have been much better if we had added a cap bank, which is based on the difference of the reactive power when the voltage is 90% and the requirement. Again, it's for the purpose of using the software and this discussion, it wouldn't make any difference, but practical ways, when you use it in real life, that's definitely something to keep in mind, that you use a larger capacitor bank or any compensator that you use on the field in order to make up for this field, because this to me doesn't look acceptable. It has to be something that even this color, this 90% reactive power, covers it here. But that's the approach. Now that you know the approach, you can go even choose much larger cap bank. Sometimes there are reasons that people want to have more capability, or sometimes there is reason that the next larger size of the cap bank is not exactly 1200, it's, let's say, 1500. Then there comes in there would be discussion and some decisions that you have to make in terms of how many steps, if these are switching cap banks, how many steps you want to add here, or if these are a STATCOM, well, that would be a different story. But the step of the cap bank, and then there is another type of a study that, again, if there is another chance, or I can continue presenting on this topic, you add each cap bank. You have to keep in mind that when you switch it in your transient stability studies, which is not the focus of this work here, you will have a voltage jump, and you have to make sure that you break it down to a small enough cap banks so that every time that you switch them in, there wouldn't be, or there would be enough jump in voltage which doesn't damage any equipment. So now I have this curve here. Next, let's take a look at the observations of this study. The cap bank contribution increases as the voltage goes up. But this is something very obvious in terms of those of us, which obviously all of us electrical engineers, we know the relationship between the cap bank voltage and the reactive power generation. The voltage goes up, the reactive power generation goes up as well, because it's V squared divided by S, Q equal to Q. So the same S that we defined here, if the voltage goes, in fact, if based on the impedance, if you put it based on the impedance, Q would be V squared divided by X. Let's put it this way. And V squared goes up, X is fixed, then Q goes up. So that's like any other impedance. The voltage across the capacitor goes up, it tends to generate more reactive power. It's something to keep in mind that if you decide and if you come up with a fixed size in terms of the reactance of the capacitor bank and you add it there, your voltage happens to be higher, then you might be able to get more reactive power out of that cap bank. It's something just to keep in mind. The cap bank size was calculated for the V100%, which I mentioned it a few times during this presentation, therefore not large enough for the 90% voltage, which is, I sort of intentionally did that so that I draw your attention to the fact that if you don't know the voltage tolerance, it might become an issue at the end. The power factor lines were drawn based on the total plant generation, not measured P at POC. So what I mean by here is that I did not consider the losses, the P losses in the plant. Let's say if you have 5 machines, 5 turbines in this example here, I said, okay, if all of them are doing 100, then I'm getting 500 kilowatt at this point, not 492. So I ignored all the losses here, and based on that I drew the line, the 95% power factor line, because that line in fact has a slope of 33%, because tangent of that angle becomes 33%, and for that ratio, for that PQ ratio, I use the real rated P value, not the P that makes it to the point of interconnection. This is again another point that I raised, and I mentioned it, that I created only one column for P, which belongs to P at V100%, but I could have done one for 100%, one for 90%, one for 110%. So this is something to keep in mind. I would strongly recommend, if you do it for a real power plant. Not only that, there would be plenty of other information that you can add to that Excel sheet. And again, I'll be happy if there are emails or questions or feedbacks that you have, or you want to reach out to me or our EasyPower for questions, or if you have suggestions, again, that would be greatly appreciated. Now, as the conclusion, any renewable plant at any size can be easily modeled in EasyPower. I described it in a very simple, straightforward fashion. I try to draw your attention to more codes and standards and history and background, and perhaps somehow I skipped the entire detailed modeling of the EasyPower. I will be happy to do that if there are demands and questions regarding that or future presentations. The point is that because I didn't want us to get much involved with the, building the one line, there were quite a few techniques that I talked about, like if you have more machines and you wanted to copy paste, that really saves a whole lot of time. But point is that I used this one, I simplified the model, and I was able to actually not only model it, talk about it, create and present the results, and it can become a comprehensive model that you can present to your local ISO, TSO in order to get the permission to build your power plant. We used wind power plants here. It could be applicable to any other type of renewables because they all have the same requirements, similar requirements when they get connected to transmission system. And the plant for this case was able to absorb enough reactive power in negative power flow mode, which obviously we talked about it enough. That being said, I would like to conclude this presentation here. I would like to stop it here and then open the panel for your questions. I have been in renewable industry quite a few years, and I have enough experience, hopefully expertise, to share with you guys when it comes to your questions. So I strongly encourage to use EasyPower. If you are not a EasyPower user, get our demo and try it. For this simple case here, all the results that you see, they came out of the EasyPower, and hopefully you will become a user of EasyPower because you see that it's a really very easy tool to learn and work with to model your power plants. So thank you very much. I stop it here and I look forward to hearing from you guys.